we need to make assumptions. Okay? So in electrostatics, the basic assumption is nothing is moving. Right? Static, 静态, stationary, everything remains non-moving. Right? So everything is not moving. And we're talking about free space now, so we might have vacuum, but we have one charge and the next charge. But they're not moving. Nothing is moving. Okay? And at this moment, there is only electric field in the space, in the free space. We only have electric field. So we only consider electric field intensity E now. This E is a vector. So later on, I will refer electric field as E field. Okay? Whenever I mention E field, I'm talking about this capitalized E vector. The official name is electric field intensity. All right. The definition of E field or E field intensity is, well, just imagine in space, right, in free space, if there's already some type of electric field, E field, then I have a charge, a particle that has certain charge. This charged particle positioned in the space filled with electric field intensity would feel some kind of force. Okay, so that is called electric force. So that electric force divided by how much of charge I'm carrying defines how strong the E field intensity is. Okay, so this is just a formal definition. So the force is proportional. So the force is proportional to how much charge you carry and multiplied by that E field intensity. Okay, so this definition is just general, right? You should have no question about it. But then, what's really relating to the physical understanding is the first postulate, written in differential form, directly tells you divergence of the E field intensity is equal to something. Oh, this is important. Why? The very reason I spent so much time teaching you and describing divergence is meant for you to relate to the electric field intensity. Divergence of the E field intensity is equal to rho divided by a constant. Rho here is the volume charge density, coulomb per meter cubed. Or within a volume, how much charge do you have, right? That is rho. So how much charge you have divided by the volume, that is your volume charge density. Epsilon 0 is just a defined constant. It's called the vacuum permittivity. It's just a constant. But look at this fundamental postulate and ask yourselves, if you have a single charge, sitting in space, not moving, what would its E field intensity look like? According to the equation, divergence of the vector field is equal to a scalar, and that scalar tells you how much charge you have. Right? Just by this simple postulate, the simple divergence relation, you already are capable of drawing some picture of the resulting field distribution. Again, tell me, what is the definition of divergence? It's too bad I cannot hear you. Otherwise, you would be saying that divergence is trying to find the net outward flux of that field over a given volume. Right? So, under this postulate, this is already telling you we know how the E field intensity looks like if you have a single charge. It is radiant. You have a charge here. Once you have a charge, the fields would look like something radiating or shooting out or shooting in. Depends on the sign of your charge. If you have a positive sign, if you have a positive charge, you have rays of electric field intensities, and these are called E field lines. 电力线. E field lines shooting out. Let me draw it for you. So if you have a positive charge, right, you would have E field lines shooting out. And it's not just two-dimensional, it's three-dimensional. It's also shooting out into your eyes, right? So you have a single charge, it's just like sun. Just like sun having sunshine. So the physical meaning is the E fields are radiant for a point charge. How do we know that? Because divergence tells you if you have a positive charge, you would have net outward flows, right? So everything is natural. What I'm trying to give you is your ability to form a physical picture just by looking at a mathematical equation. Divergence tells you you have to go out. So if you have a positive value, your field lines are shooting out. So what happens if your charge is negative? Then your divergence is flowing in, right? Your fields are flowing in, and therefore your charge is negative, field lines going in. Again, everything is three-dimensional, okay? So that's the first fundamental postulate. For electric fields, divergence, once you have the field, divergence is not zero. What does that imply? And look again at this equation. What is the source for electric field? This equation also tells you once you have a charge, you have field, right? So the source for an electric field distribution is charge distribution. Secondly, it tells you if you have a single charge, you have a sun-like radiating pattern. Okay? Now think, if you have a radiating, well, for example, you have a single charge and you have a radiating E field pattern, what other mathematical description or physical description would you be using to describe it? So in my personal opinion, You only need to understand the first postulate, and then you understand the second postulate. They are actually saying the same thing. The second one, well, let's come back to the null identities. Divergence is not zero. What does that mean? And the field divergence is not zero, and I'm telling you everything is radiating outwards in a unidirection. This implies electric fields are conserved fields, just like gravity. So the second one tells you, since your field for a single charge is radiating, like how sun shines, coming out of sun, so the curl is zero. These two are like twins. You have one, you must have the other. Okay. So curl of E field is zero, means electric fields are conserved. Right? So the physical meaning is they are conserved, so they are not rotational. There's no circulating component. For electric fields, you don't have really circulating components. If you do have circulating components, it's non-conserved. Right? Then curl of E is not equal to zero. And that violates our understanding. Right? So this is coming directly from this. You have radiating field patterns, so you don't have circulating fields. Therefore, curl of E is zero. Definitely. Right? Now, can you answer my previous question? I told you, electric field is associated with one of the null identities. So there are two. I'm such a nice teacher, I'm telling you the answer. Curl of E field intensity, the vector, is always zero. So you, at this moment, should be capable of relating that to the null identity. Curl of a vector field is zero, so that vector field can be written as the gradient of a scalar function. And that scalar function is potential, voltage, that we always talk about. Okay? So electric field is associated with the first null identity. Magnetic field, on the other hand, is related, or directly related to the second null identity. So if you're smart, and if you understand my lecture contents, you should have a physical picture now. E fields are radiating out. Magnetic fields are circulating. Right? Straightforward. Vector analysis is telling you a lot about our world. Okay? Now, these two postulates, divergence E is equal to rho divided by epsilon 0, and curl of E is equal to 0, they're universal. So no matter which orthogonal coordinate system you decide to use, they always remain true. Okay? They're always true. Now, knowing the differential form for the two postulates is really not helping us a lot, right? Because eventually, we should be capable of calculating the fields, the E field distribution, as a function of space whenever we know the charge distribution. But the differential form is not giving a lot of information. So for this particular case, we want to know the macroscopic description of E field intensity, which means we want to have the postulates expressed using integration, right? So again, differential form tells you the microscopic point by point what is happening, but the integral form means overall. I can just describe it, okay, in a macroscopic view. Do we have the mathematical tool for that? It's still here. Because E field is associated with divergence, so why don't we invoke divergence theorem to give us a nice and easy fundamental postulate in the integration form. So divergence of E is equal to rho, the volume charge density divided by a constant. And because you're so smart and you're so hardworking, you learned very solidly, so you know that we already covered divergence theorem. Divergence theorem tells us if you want to evaluate the divergence point by point, and we integrate over the entire value. So point by point, I know the divergence, but over the entire value, do I need to perform the value integration? No, we don't. We only need to evaluate the vector field making a closed surface integration to evaluate the same thing, right? So now we replace A by E. So divergence of E is equal to rho divided by epsilon 0, and we perform the value integration. This is easy, because that's the total charge, right? So Gauss's law is basically saying the fundamental postulate, the very first one, if you know how much charge you have, basically you know how your E field distribution would look like. Okay? This is extremely important. Using this integral form is much easier for us to derive how the E field distribution looks like. Differentiation form is looking at the microscopic view. It's not really helpful. So Gauss's law is nothing more than the first fundamental postulate, but using a different viewpoint. This is microscopic. Gauss's law is a macroscopic 巨观 point of view. All right, curl of E is equal to 0. Why do professors always teach divergence theorem and Stokes theorem? Because they're useful. Whenever you have curl operation, you use Stokes theorem, right? Instead of calculating the curl over the entire surface, you only need to evaluate the field over the closed loop. So we apply Stokes theorem. This A is replaced by E. Curl of E equals to 0. So that means when you have electric field, you walk in a closed path. This is 0. It's always 0. So again, this is telling you electric fields are conserved fields. So in this electric fields, you start from a certain point, you walk, whatever path, you come back to the same point, you gain nothing, you lose nothing. It's conserved. Okay? So how can this be really applied to our daily lives? It's like saying nothing, right? It's just saying the field is conserved. But it's saying a lot. If you still remember, in electric circuit, you learned about Kirchhoff's voltage law. Oh, that's extremely useful. This is equivalent. E field, making some work, means your energy or potential. It's like voltage. So basically, if you have a closed loop, all the voltage drops would sum up to 0. So that is equivalent form of Kirchhoff's voltage law. So the second postulate directly contributes to Kirchhoff's voltage law. Right? So I think time's pretty much up. And instead of going into a new section, I would rather stay here and see whether you have questions. So on Wednesday, we can pick up the progress from Coulomb's law. So are there questions from the distant audience?